Have you ever stepped outside and just felt the sheer power of the air moving around you? Maybe the warmth of the sun or, the bite of the cold.
Hmm.
Climate-wise, some places are hot and wet, others dry and cold, or why wind blows the way it does. It feels incredibly vast, doesn't it? So complex.
It really does. But, at its core, it's not totally random or mysterious.
Right.
It's actually built from specific fundamental ingredients and forces. They all interact in what's, well, a surprisingly elegant system.
Think of it as Earth's intricate machinery, maybe.
Yeah.
Driven by energy,
Right.
sculpted by physics and geography.
That's a great way to put it. And understanding those foundational bits, those elements of the system, it really gives you a different perspective on the world around you.
Yeah, like why some landscapes look the way they do, or why certain weather patterns just dominate specific regions.
Exactly.
And that's exactly what we're diving into today. Our source material, it comes from these excerpts of physics and human geography textbooks.
Good foundational stuff.
Our mission, really, is to take these core concepts presented in the pages, from the very air we breathe, right up to the global patterns that shape whole continents and pull out the most important nuggets.
Kind of like getting the essential toolkit.
Yeah, exactly. The essential toolkit for understanding Earth's climate system. We want to show you how these building blocks create this incredible variety of climates we see on our planet.
And these sources, they give us that fundamental physical and geographical context.
Right.
They explain why heat behaves the way it does in the atmosphere,
Right.
why air moves from one place to another, and, crucially, how all those basic principles combine to create the distinct climate zones we see across the globe.
Okay, so let's unpack this together. We'll guide you through it, highlighting the interesting details.
And connecting the dots, hopefully revealing that bigger picture.
Let's dive in. So
Yeah.
where do we start? The foundation, right? The atmosphere.
Absolutely. The very air surrounding our planet. The source material describes it pretty straightforwardly, a mixture of gases, water vapor, and tiny particles.
Our planet's blanket, essentially.
That's a good image. It's our protective blanket, and it's really the crucial starting point for understanding climate. Because, well, all climate phenomena happen within it.
Right, it's the stage.
Yeah.
And this blanket, it's not just one uniform thing, is it? The text says it has a structure, like layers.
Yes, a vertical structure. The layer closest to us, the one we live in, where pretty much all the weather we actually experience happens, that's the troposphere.
Troposphere, okay.
It goes up about, what does it say, 6 miles or so from the surface. And what's really key about this layer is that the temperature typically decreases as you go higher.
Gets colder the higher you climb a mountain, basically.
Precisely. And that characteristic, that cooling with altitude, it's fundamental. It's a major driver for processes like convection. Warm, less dense air near the surface rises.
Into colder, denser air above.
Exactly. And as it rises, it cools, leading to condensation, clouds, all that good stuff.
Okay. And above the troposphere.
Above that is the stratosphere. It goes up much higher, maybe 50 miles or even more. The source points out it's generally very clear there, not much water vapor.
Less turbulent, maybe.
Definitely less turbulent than the troposphere. And interestingly, kind of counterintuitively, the temperature in the stratosphere actually increases with height.
Really? Why is that? Does the text say?
It doesn't go into the why in detail here, but we know it's primarily because the ozone layer sits in the stratosphere and it absorbs ultraviolet radiation from the sun. That absorption process heats things up.
Ozone, which is, of course, vital for protecting us down here.
Absolutely essential.
Yeah.
And then way, way up, several hundred miles high, you get the ionosphere.
That sounds very sci-fi.
Ha! Yeah, a bit. It's mentioned as being electrically conducting, important for radio communication. And it's up in these higher reaches, the stratosphere and beyond, where we have weather balloons and satellites doing their thing, collecting critical data.
Okay. So, just knowing about these layers, the busy troposphere, the clear stratosphere, the outer reaches, it helps paint a picture of the vertical stage where climate plays out.
It really does. It provides context.
So what's this atmospheric blanket actually made of? The source gives the breakdown.
Yeah, the basic composition, mostly nitrogen, about 78%, and oxygen, around 21%.
The air we breathe, essentially.
Those are the big ones, the stable components. But, it's often the minor ingredients that have major effects. That remaining less than 1% includes other gases like argon, carbon dioxide.
And crucially, water vapor.
Yes, crucially, water vapor. The source really emphasizes that its amount is highly variable.
It changes a lot depending on where you are and when.
Exactly. And it's not just a gas. It exists as liquid, think raindrops, cloud droplets, and solid snow, hail, ice crystals. Plus, the atmosphere holds other tiny suspended things like smoke particles, dust.
Which are important too, right? Like for clouds forming.
Absolutely vital. Those particles act as nuclei, little seeds for water vapor to condense onto. But focusing on water vapor's variability, that's just central to understanding climate differences across the globe.
How so?
Well, in its gaseous form, it's the most significant greenhouse gas naturally. It's the stuff that forms clouds, which reflect sunlight and trap heat. And maybe most importantly, its phase changes, evaporating, condensing, freezing, involve absorbing or releasing enormous amounts of energy.
Latent heat, right?
Precisely, latent heat. That energy transfer drives weather systems. So a region with loads of water vapor behaves completely differently, climatically speaking, than a dry desert region.
Got it. Okay, so we have the atmosphere layers, gases, variable water vapor. But what powers it all? Where does the energy come from?
The source is crystal clear on this. The only significant source of energy for the Earth's atmosphere and surface is incoming solar radiation, what we call insolation.
Insulation from the sun.
Yep, all the way from the sun, nearly 93 million miles away. It travels through the vacuum of space as radiant energy.
And this solar radiation, it's not just one thing, is it? The text breaks it down.
Right. It specifies three main parts. Visible white light, which is what we see.
The most intense part, it says.
Yes. Then there are the ultraviolet, or UV, rays. Higher energy, they're the ones that affect our skin, cause sunburn with too much exposure.
Right. Nasty stuff if you get too much.
And then there are the infrared, or IR, rays. Lower energy, often what we feel as heat. The source notes they can penetrate fog and dust, which is interesting. But taken together, all this energy reaching Earth is what we call insolation.
Okay, now here's a fascinating bit. Not all that energy actually sticks around or even reaches the ground, does it? The source gives percentages for the Earth's energy budget.
Yeah, this is really fundamental. Out of the total 100% of incoming solar radiation hitting the top of the atmosphere, about 35% gets sent straight back to space.
Just reflected away. By what?
By a few things. Tiny particles in the air, aerosols, dust. Clouds are big reflectors, and even the Earth's surface itself, especially bright surfaces like snow and ice.
And this reflection, or scattering, it mentions that's why the sky is blue.
That's the one. It's the scattering of sunlight by air molecules, particularly the blue wavelengths. So yeah, 35% is effectively lost back to space straight away.
Okay, so 35% bounce back. What happens to the other 65%?
Well, another chunk, the source is about 14%, is absorbed directly by the atmosphere itself. Gases like water vapor, carbon dioxide, ozone, they grab some of that incoming energy as it passes through.
Okay, so 35% reflected, 14% absorbed by the air. Doing the math, that leaves 51%.
Exactly right. The remaining 51%, just over half, is what successfully makes it all the way down to the Earth's surface. It hits the land, the oceans. It might arrive directly or maybe after being scattered or diffused a bit on the way down.
And this is the energy that actually warms the ground and the water.
That's the energy that does the primary heating of the surface. But it doesn't just stay there.
No.
No, the source points out that this 51% absorbed at the surface is then transferred back up into the atmosphere.
How does that happen?
Through a few key processes. Conduction, direct heating of the air molecules right next to the warm ground. Convection, the warm air becomes buoyant and rises, carrying heat upwards. And also through the transfer of latent heat by water vapor as it evaporates from the surface.
So the surface becomes like a radiator heating the air above it.
In a way, yes. And a really crucial point highlighted in the material is that the rate at which this heating and energy transfer happens is fundamentally different depending on what the surface is made of. Specifically, the difference between land and water.
Ah, yes. This seems super important. Land heats up much more quickly than water, right?
Oh, much, much more quickly. The text explains why. Water is transparent, so sunlight penetrates deeper into it, spreading the energy over a larger volume. Plus, water has a higher specific heat capacity. It takes more energy to raise its temperature, and water mixes. Currents distribute the heat.
Whereas land is opaque, so the energy is concentrated right at the surface.
Exactly. The consequence is, for the same amount of sunshine, the surface temperature of land will shoot up way more than the surface temperature of water. Think about walking on hot sand versus stepping into the sea on a sunny day.
Oh yeah, big difference.
And just as land heats up faster, It also cools down much faster than water when the sun goes down. Water holds on to its heat for longer.
So land areas have these bigger swings in temperature day to night, summer to winter.
Much larger and more rapid temperature fluctuations compared to places near large bodies of water.
And this difference, this fundamental difference in how land and water handle energy, you're saying that's a primary driver of, well, everything else.
Pretty much. It's a primary driver of atmospheric circulation. It creates temperature differences, gradients between land and sea, between different latitudes. These temperature differences create pressure differences.
High pressure, low pressure.
Right. And air flows from high to low pressure. That flow is wind. So ultimately, every gust of wind, every major air current, it traces its origins back to this incoming solar energy and the uneven way Earth's surfaces absorb and release it. It really is the engine driving the whole climate system.
Wow. Okay. It's not just sunlight hitting Earth. It's this whole dynamic process of energy capture, transfer, redistribution.
Okay.
So we have the atmosphere, we have the energy. What are the actual things we measure when we talk about climate? And what influences them?
The sources point to four main dominant elements that define the climate of a place. These are temperature, precipitation, pressure, and winds.
The things we feel and see every day.
Exactly. These are the core elements. And then shaping these elements are a whole range of influencing factors that vary from place to place.
Let's see, the list includes latitude, altitude, continentality, that land versus water thing.
Ocean currents, insulation, which we've just covered.
Prevailing winds, slope and aspect, like which way a hill faces.
Right. And even natural vegetation and soil type.
Wow, quite a list. So it's the unique mix of these factors at any given spot that determines its specific climate.
That's the idea. Let's tackle temperature first, since we were just talking about energy and heating. The source rightly stresses its importance. Temperature isn't just about feeling hot or cold.
No. What else?
Well, it directly impacts evaporation rates, how much water turns into vapor. It affects condensation rates, too, and therefore it governs things like humidity levels and the potential for rain or snow.
Makes sense. And the most fundamental factor influencing temperature globally has to be latitude, right? How far north or south you are.
Absolutely. Think about the angle the sun's rays hit the Earth, near the equator.
They come in almost straight down.
Pretty much perpendicular, so that energy is concentrated over a smaller area. Plus, the rays travel the shortest possible path through the atmosphere, so less energy gets scattered or absorbed on the way.
But as you go towards the poles,
the angle gets much lower, much more oblique. The same amount of energy gets spread out over a much larger surface area, and those rays have to travel a longer path through the atmosphere, losing more energy before they even reach the ground.
like shining a flashlight straight down versus at an angle.
Perfect analogy. That difference in the intensity of insolation is the #1 reason it's generally warmest near the equator and gets progressively colder as you head towards the poles. It's the master control on global temperature.
Okay. Then there's altitude, going up a mountain.
Yep. The text is clear. Temperature decreases with increasing height above sea level. It's a consistent phenomenon called the lapse rate.
Is there a standard rate?
The source gives a useful approximation. About 1 degree Fahrenheit drop for every 300 feet you go up, or roughly 0.6 degrees Celsius for every 100 meters.
Which is why mountaintops are snowy even near the equator sometimes.
Exactly. As you go up, the air pressure drops, the air expands, and expanding air cools down. It's a basic physical principle.
Continentality, we touched on this, being inland versus near the coast.
Right. Inland areas, far from the moderating effect of oceans or large lakes, experience a much greater range of temperatures through the year.
Hotter summers, colder winters.
Generally, yes, because land heats up fast in summer and cools down fast in winter. Coastal areas at the same latitude have those temperature swings dampened by the nearby water, which warms and cools much more slowly. So think London versus, say, Winnipeg at similar latitudes. London's maritime climate is much less extreme.
Ocean currents, too. They move heat around.
They act like giant conveyor belts for heat, absolutely. Warm currents, starting near the equator, carry immense amounts of heat poleward. The classic example mentioned is the Gulf Stream, or North Atlantic Drift.
That warms up Western Europe.
Massively. It keeps ports in the UK and Norway ice-free in winter, even though they're quite far north. Conversely, cold currents flowing from the poles towards the equator make coastal areas cooler than you might expect, like the Labrador Current chilling the coast of eastern Canada and New England.
And the wind blows that influence inland.
Often, yes. Prevailing winds blowing over a warm current bring warmer air inland, and winds over a cold current bring cooler air.
Slope and aspect, which way a slope faces. That seems more local.
It is more local, but it can be significant. In the northern hemisphere, a south-facing slope gets much more direct sunlight through the day than a north-facing slope.
So it's warmer.
Warmer and often drier because more water evaporates. This affects where trees grow best, where snow melts first, even where people historically chose to build settlements. The steepness of the slope also matters. Steeper slopes shed water faster, affecting soil moisture and vegetation, which indirectly ties back to temperature.
And the ground cover itself. Vegetation and soil type.
Yep, they play a role too. A dense forest canopy, like the Amazon example in the source, blocks a lot of sunlight from reaching the ground, keeping the forest floor cooler and shadier.
Plants also cool things down through transpiration.
Evapotranspiration, yes. Releasing water vapor cools the surrounding air, and the soil itself matters. Damp soil stays cooler than dry soil. Different soil types, sandy, clayey, hold heat and moisture differently, creating little microclimate variations.
Okay. One last temperature factor mentioned. Temperature inversion. What's that?
This is interesting. It's when the normal pattern reverses. Instead of getting colder with height, there's a layer of air where the temperature actually increases with height.
How does that happen?
Often happens in valleys on clear, calm nights. The ground cools off really fast by radiating heat away. The air right next to the ground gets cold and dense, and it pools in the valley bottom like water. Warmer, lighter air ends up sitting on top of this trapped layer of cold air.
So the coldest air is actually down low. That feels wrong.
It does feel counterintuitive, but it happens frequently, and it can trap fog or pollution down in the valley bottoms because the stable layer prevents mixing. It's a neat example of local conditions overriding the general lapse rate rule.
Fascinating. Okay, that's a really thorough look at temperature and its controls. Now let's switch gears to water falling from the sky. Precipitation. Precipitation. Basically, any form of water, liquid, or solid that falls from clouds and reaches the ground. Rain, snow, sleet, hail.
And how does it form? The basics.
It all starts with air rising. Warm, moist air rises, and as it goes up into lower pressure, it expands and cools.
Colder air can't hold as much water vapor.
Exactly. So as the air cools, the invisible water vapor within it starts to condense, turning back into tiny liquid water droplets, or, if it's cold enough, tiny ice crystals.
And they need something to condense onto.
Usually, yes. Tiny particles floating in the air dust, salt from the ocean, pollen, pollution, they act as condensation nuclei, little surfaces for the water vapor to grab onto.
And these tiny droplets or crystals make clouds.
Millions and billions of them suspended in the air form the clouds we see. Then, inside the cloud, these droplets or crystals bump into each other, stick together, and grow larger.
Until they're too heavy to stay up. Right. When they get heavy enough that the air currents within the cloud can no longer support them, gravity wins, and they fall to the ground as precipitation.
The source lists the main types. Rain is just liquid droplets. Snow is ice crystals. Sleet is...
Sleet is basically raindrops that freeze into little ice pellets as they fall through a layer of freezing air near the surface.
Okay. And hail. That sounds more dramatic.
Hail is definitely more dramatic. Hailstones are chunks of ice formed inside intense thunderstorms, specifically cumulonimbus clouds with strong updrafts.
How do they get so big?
The updrafts toss these ice particles up and down within the storm cloud. Each time they get carried up high into the freezing levels, they collect more supercooled water, which freezes onto them, adding a layer. This can happen multiple times, creating large, layered hailstones until they finally become too heavy for the updrafts and plummet to the ground. The source notes they can cause significant damage.
Ouch. Okay. It also mentions rime frost briefly.
Yeah, that's a bit different. Formed when supercooled water droplets in fog or mist freeze directly onto surfaces. Less common is falling precipitation.
So the basic recipe is lift moist air, cool it, condense it, let the drops crystals grow, then let them fall. But how does the air get lifted? The source gives three main ways, three types of rainfall.
Correct. The first is convectional rainfall. Think hot, humid days.
Like summer thunderstorms.
Exactly. The sun beats down, heating the ground intensely. The air right above the ground gets heated, becomes less dense, more buoyant, and starts rising rapidly. These are powerful updrafts called convection currents.
Like bubbles rising in boiling water, but with air.
That's a perfect visual. As this warm, moist air shoots upwards, it cools quickly at higher altitudes. Water vapor condenses, forming those big, tall, puffy cumulonimbus clouds.
The thunderhead clouds.
Those are the ones. They can grow vertically for miles, holding enormous amounts of moisture. When the condensation process goes into overdrive, you get heavy, often torrential rain, frequently with lightning and thunder. The The source says this type is very common near the equator, where heating is intense all year, and also typical for summer afternoons in temperate regions like ours.
Okay, convection. What's the second type? Orographic.
Orographic rainfall, also called relief rainfall. This one is all about topography, specifically mountains.
Mountains getting in the way of the wind.
Pretty much. When moist air blowing across the land encounters a mountain range, it's forced to rise up the slope on the side facing the windward side.
And rising air cools.
Rising air cools, leading to condensation, cloud formation, and usually significant precipitation, rain or snow falling on that windward slope. The mountain effectively squeezes the moisture out of the air.
So the windward side gets lots of rain. What about the other side?
The other side, the leeward side. As the air, having dropped its moisture, descends the leeward slope, it gets compressed by the increasing air pressure at lower altitudes. Compressed air warms up. This is called adiabatic warming.
So it's descending, warming, and it's already lost its moisture.
Exactly. It becomes warm and very dry. This creates what's known as a rain shadow on the leeward side of the mountain.
An area with much less rain.
Often significantly less, sometimes creating desert or semi-desert conditions right next to a lush, wet windward slope. The source gives examples like the Andes, the Western Ghats in India, even parts of the UK and New Zealand.
Fascinating. Okay, third type. Cyclonic or frontal rainfall.
This type is associated with large, low-pressure systems. We often call them depressions or cyclones, which are very common in the temperate latitudes.
The mid-latitudes where we live.
Right. These systems form where different large bodies of air, called air masses, meet. Typically, it's a warmer, moister air mass bumping into a colder, drier air mass. The boundary between them is called a front.
Warm front, cold front.
Exactly. Now, the warmer air is less dense, it's lighter than the cold air. So when these air masses collide, the warmer air is forced to slide up and over the wedge of colder, denser air.
It gets lifted again, but by the collision, not by a mountain or direct heating.
Precisely. It's lifted along the frontal boundary. And again, as that warm, moist air rises, it cools, water vapor condenses, forming extensive sheets of cloud and producing precipitation, often widespread, steady rain or snow associated with the passage of the front. This is the mechanism behind much of our weather in places like North America and Europe.
So lifting mechanisms are key. Intense heating from below, convection.
Yeah.
Forcing up by terrain, orographic, or forcing up over another air mass, frontal.
Those are the three main triggers for significant precipitation described in the source. They explain most of the world's rainfall patterns.
Got it. Okay, atmosphere, energy, temperature, precipitation. Let's move on to the big drivers of movement. Pressure systems and winds.
Right, air pressure and wind. Fundamentally, air flows from areas of higher pressure to areas of lower pressure, trying to even things out.
And what creates those pressure differences in the first place?
It really comes back to the uneven heating of the Earth's surface that we talked about. Warm air tends to rise, leaving slightly lower pressure at the surface below it. Cold air tends to sink, piling up and creating higher pressure at the surface.
And there's a global pattern to this. The source shows these world pressure belts.
Yes, there's a large-scale, somewhat idealized pattern. Around the equator, roughly 0 to 10 degrees north and south latitude, you have the equatorial low-pressure belt.
Low pressure because it's hot and air is rising.
Exactly. Intense solar heating leads to constantly rising air, creating this zone of low pressure. Sailors historically called this area the doldrums.
Why doldrums?
Because the main air movement is up, not sideways. So surface winds are often very light and unpredictable, which was terrible for sailing ships relying on wind. It's a zone where surface winds converge towards the equator.
Okay. Then moving away from the equator, around 30 degrees north and south, we find the subtropical highs.
Right. Here, the air that rose at the equator cools down at high altitudes, moves poleward, and then sinks back towards the surface around these latitudes.
Sinking air means high pressure.
Sinking air means high pressure. These are often zones of clear skies and dry conditions associated with many of the world's major deserts. Historically, these were the horse latitudes.
Horse latitudes, another sailing term.
Apparently so. Again, associated with calm winds due to the sinking air, potentially forcing ships to jettison cargo, including horses, to conserve water. These are zones where surface air diverges, spreading outwards.
Further poleward again, around 60 degrees north and south, the temperate lows.
Yes, these are really dynamic zones. This is generally where warmer air moving poleward from the subtropics meets colder air sliding down from the poles.
The fronts we talked about for cyclonic rain.
Precisely. That meeting and the lifting of warmer air creates belts of lower pressure. These zones are associated with lots of storminess, the mid-latitude cyclones, and variable weather. It's a zone of convergence where surface winds come together.
And finally, right at the poles, 90 degrees north and south.
The polar highs. Extreme cold makes the air very dense, so it sinks, creating persistent high pressure over the polar regions. Very cold and very dry conditions typically.
So low pressure at the equator and 60 degrees where air rises, high pressure at 30 degrees, and the poles where air sinks, like giant circulation cells.
That's the basic idea, yes. A simplified model of global atmospheric circulation. And the air flowing at the surface, moving from those high-pressure belts towards the low-pressure belts, creates the major prevailing wind systems on Earth, the planetary winds.
Let's start with the trade winds.
Okay. The trade winds blow from the subtropical highs, around 30 degrees, towards the equatorial low, near 0 degrees.
From high to low pressure. Makes sense.
But they don't blow straight south or north because of the Earth's rotation.
The Coriolis effect.
Exactly. They get deflected. In the northern hemisphere, they blow from the northeast. In the southern hemisphere, they blow from the southeast. They're called trade winds because they were famously reliable for sailing ships on trade routes. They blow mostly over warm tropical oceans, so they tend to be warm and pick up moisture.
Okay. Next up, the westerlies.
The westerlies blow from the subtropical highs, again around 30 degrees, but this time they blow toward the temperate lows around 60 degrees latitude.
So moving poleward from the highs.
Right, and again, Coriolis deflects them. They come from the southwest in the northern hemisphere and the northwest in the southern hemisphere. Hence, westerlies, they generally blow from west to east in the mid-latitudes.
And these are important for our weather.
Hugely important in the mid-latitudes. They steer weather systems, bring moisture from oceans onto the western sides of continents, influencing places like Western Europe and the Pacific Northwest of North America. They are known for being quite variable and strong.
And the source mentions those evocative names for them in the southern hemisphere.
Ah, yes, the roaring 40s, furious 50s, and shrieking or stormy 60s.
Why so intense down there?
Primarily because there's much less landmass interrupting the ocean flow in the southern hemisphere at those latitudes. The westerlies can just rip across vast stretches of ocean without being slowed down by continents, building up incredible speed and consistency, leading to notoriously rough seas and strong winds.
Wow. Okay, the last set. The polar easterlies.
These blow from the cold polar highs near the poles towards the temperate lows around 60 degrees. Deflected by Coriolis, they come from the northeast in the northern hemisphere and the southeast in the southern hemisphere.
So generally blowing from east to west near the poles.
Right. And originating from the poles, they are typically extremely cold and dry winds.
Now you keep mentioning this deflection, the Coriolis force. It's not actually pushing the wind, is it?
That's a key point. It's not a real force in the sense of a push or pull. It's an apparent force or an effect that arises because we are observing motion on a rotating planet.
The Earth is spinning underneath the moving air.
Essentially, yes. As air starts moving from high to low pressure, the Earth rotates beneath it. From our perspective on the rotating surface, the path of the air appears to curve.
And the direction of the curve is consistent?
Yes. To the right of the direction of motion in the northern hemisphere, and to the left of the direction of motion in the southern hemisphere.
The source mentions Buys-Ballot's law.
Ah, yes. That's a practical rule of thumb derived from the Coriolis effect. It states that if you stand with your back to the wind, the low-pressure center will be on your left in the northern hemisphere and on your right in the southern hemisphere. It helps meteorologists locate pressure centers.
So Coriolis is what bends the straight high to low pressure flow into those curved paths of the trade winds and westerlies.
Exactly. It fundamentally shapes large-scale atmospheric circulation. It's also why storms like hurricanes and mid-latitude cyclones rotate the air, spiraling into the low-pressure center gets deflected.
Fascinating. Okay, so we have the global patterns. Let's zoom in a bit to some more dynamic phenomena, local winds and storms, starting with land and sea breezes.
Right. These are much smaller scale daily wind cycles you find along coastlines, driven again by that differential heating of land and water we talked about, but operating over a 24-hour cycle.
Okay, so during the day, land heats up faster than the sea.
Much faster. The air over the warm land heats up, expands, becomes less dense, and starts to rise. This creates a small area of lower pressure right over the land near the coast.
And the air over the cooler sea is at higher pressure.
Relatively higher pressure, yes. So what happens? Air flows from the higher pressure over the sea towards the lower pressure over the land. That onshore flow is the sea breeze.
That cool breeze you feel at the beach on a hot afternoon.
That's the one. It brings welcome relief.
And then at night.
It reverses. The land cools down much faster than the sea, which retains its heat longer. So the air over the cool land becomes denser and sinks, creating local high pressure. The air over the relatively warmer sea is now at lower pressure and tends to rise.
So the wind blows from the land out to the sea.
Correct. That's the land breeze. The source notes that sea breezes are usually stronger than land breezes, probably because the temperature difference between land and sea is often greater during the day due to intense sunshine.
Okay. The source also mentions monsoons, calling them a larger scale version of land and sea breezes.
That's a really good way to understand them. Monsoons are driven by the same principled differential heating of land and ocean, but on a vast continental scale and over seasons rather than just day and night.
So in summer, the huge landmass of a continent, like Asia, gets incredibly hot compared to the surrounding oceans.
Extremely hot. This creates a massive, persistent area of low pressure over the continent. Meanwhile, the air over the relatively cooler ocean is at higher pressure.
So the wind blows from the ocean onto the land.
Yes, a huge inflow of moist air blows from the ocean towards that continental low-pressure zone. This onshore flow brings the incredibly heavy, prolonged rainfall associated with the summer monsoon vital for agriculture in places like India, Southeast Asia, parts of Africa.
And then in winter, the continent cools down drastically.
Much colder than the ocean. This creates a strong, large area of high pressure over the land. Air then flows outwards from this continental high towards the relatively warmer, lower pressure over the ocean.
And this winter monsoon is dry.
Typically very dry and often cold as the air originates over the cold landmass. It's a dramatic seasonal reversal of wind direction and associated weather.
Wow. The source also mentions Fawn and Chinook winds. What are they?
These are interesting. They are warm, dry winds that blow down the leeward slopes of mountain ranges. They're closely related to the orographic rainfall process.
So air loses moisture going up one side.
Yes, it cools and precipitates on the windward side. Then, as that now dry air descends the leeward slope, it gets compressed and warms up very rapidly due to that adiabatic heating we mentioned.
So it arrives at the bottom warm and dry.
Very warm and very dry. They can cause dramatic temperature jumps in a short time. They're famous as snow eaters because they can sublimate or melt snow cover incredibly quickly. The source mentions the Fawn in the European Alps and the Chinook in the North American Rockies as classic examples.
Okay, now for the really big weather events, cyclonic activity storms.
Right. Cyclones, broadly speaking, are low-pressure systems where winds spiral inwards towards the center. The source differentiates between the intense tropical ones and the larger mid-latitude ones.
Tropical cyclones, we know them as hurricanes, typhoons.
Hurricanes in the Atlantic and Northeast Pacific, typhoons in the Northwest Pacific, and cyclones in the Indian Ocean and South Pacific. They are incredibly powerful, rotating storm systems that form over warm tropical ocean waters.
They need that warm water energy.
Absolutely. Usually, sea surface temperatures need to be above about 26.5 degrees Celsius or 80 degrees Fahrenheit to fuel their development. They feature extremely high sustained winds, the source says, over 100 miles an hour, often much higher torrential rain, and powerful thunderstorms spiraling around a central point.
And that center is the eye.
Yes, the eye is a fascinating feature. It's a relatively calm, clear area at the very center of the storm, typically 10 to 30 miles across, where air is actually sinking slowly. Winds are much lighter inside the eye, but surrounding the eye is the eye wall, where the most intense winds and heaviest rain occur.
And they're quite compact but destructive.
Relatively compact, yes, maybe 50 to 200 miles across according to the source, much smaller than mid-latitude storms. But their concentrated power, high winds, flooding rain, and the storm surge they push ashore can cause catastrophic damage.
Okay, tornadoes were also mentioned, even more violent.
On a localized scale, yes, tornadoes are arguably the most violent storms on Earth. They appear as dark, rotating funnel clouds extending down from severe thunderstorms, often associated with the cold fronts of larger mid-latitude cyclones.
But they're very narrow.
Extremely narrow path of destruction, maybe only a few hundred feet to perhaps 1,400 feet wide, as the source notes. But within that narrow path, wind speeds can be phenomenal. The source mentions potentially reaching 600 miles per hour in extreme cases, capable of obliterating structures. They form and dissipate very quickly and are most common in the central U.S., the tornado alley.
Terrifying. Then there are depressions or mid-latitude cyclones. These are the larger systems.
Yes, these are the large, low-pressure systems typical of the temperate zones, like the ones that bring us our day-to-day weather changes. They form along the fronts where warm and cold air masses meet.
And winds spiral inwards.
Inwards towards the low-pressure center, yes. Deflected by Coriolis, they rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. They bring widespread clouds, precipitation, rain or snow depending on temperature, and shifting winds as the warm and cold fronts associated with them sweep through.
And they're much bigger than hurricanes.
Much larger, yes. The source says anywhere from 150 to 2,000 miles across. They also tend to move more slowly than tropical cyclones. So, while maybe not having the extreme peak wind speeds of a hurricane, they affect a much larger area for a longer period, bringing prolonged spells of unsettled weather.
They're the main weather makers in the mid-latitudes.
Absolutely. And the opposite of these low-pressure cyclones.
Anticyclones, high-pressure systems.
Correct. In an anticyclone, air is gently sinking towards the surface. Pressure is highest at the center, winds spiral outwards from the center, clockwise in the northern hemisphere, counterclockwise in the southern hemisphere.
And what kind of weather do they bring?
Sinking air warms and dries out as it descends, which inhibits cloud formation. So anticyclones are typically associated with calm, stable conditions, fine weather, clear skies, light winds. They can bring settled spells lasting for days. In winter, those clear skies allow for rapid nighttime cooling, often leading to frost or fog.
So highs bring fine weather, lows bring stormy or wet weather. A bit simplistic, but generally.
As a general rule of thumb, it holds true quite often. These pressure systems are fundamental to understanding weather patterns.
Okay, we've built up quite a picture. The atmosphere, energy, temperature factors, precipitation types, global winds, local winds, storms. Now, how does all this complexity come together to create the distinct climates we see around the world? The source talks about world climate types.
Yes, after explaining all the ingredients and processes, it moves to classification. Trying to group regions with similar climatic characteristics is really useful for understanding global patterns, especially how climate influences things like agriculture and natural vegetation.
So these climate zones are areas where the interplay of all those elements, temperature, rain, winds, etc., results in a recognizable, consistent type of climate.
Exactly. The source provides a table and a map showing major climate zones based on these factors. It's a way of summarizing how all the pieces fit together geographically.
Let's look at a few examples from the table to illustrate. How about the hot, wet equatorial climate? Right near the equator, 0–10 degrees north and south.
Okay, the table says, hot, very wet, heavy rain all year round, over 80 inches, supporting equatorial rainforests.
So connecting that back, high direct insolation all year means consistently hot temperatures.
Right. And it's in the equatorial low-pressure belt, the doldrums, zone of convergence, and rising air.
Which leads to
intense surface heating triggers strong convection. That rising moist air cools, condenses, forms massive clouds, leading to heavy convectional rainfall almost daily. Consistent heat plus abundant moisture equals perfect conditions for rainforests.
Makes sense. Now, contrast that sharply with the desert climate, listed around 15–30 degrees north and south. Hot, warm, very little rain, maybe 5 inches. Desert scrub.
Okay, those latitudes, 15–30 degrees, put these regions smack bang in the middle of the subtropical high-pressure belts.
The horse latitudes, where air is sinking.
Precisely. Persistent sinking air warms as it descends and becomes very dry. This actively suppresses cloud formation and rainfall. So even though these areas often get intense sunshine insolation, the large-scale atmospheric circulation prevents rain, leading to deserts. The source also notes their common location on the western sides of continents in the tropics, linked to cold ocean currents offshore enhancing the dryness.
Okay, moving poleward. Mediterranean type, 30–45 degrees north and south. Warm winter rain around 35 inches, dry summers. Mediterranean forest shrub.
Ah, the med climate. This is a classic example of seasonal shifts in the pressure belts being key.
How so?
In winter, the main storm tracks and the westerly winds shift equatorward, bringing moisture and cyclonic frontal rain to these latitudes. But in summer, the subtropical high-pressure belt expands and shifts poleward, dominating these regions with its dry, sinking air.
So they get westerly rains in winter, but dry high pressure in summer.
Exactly. That distinct wet winter-dry summer pattern is the hallmark of the Mediterranean climate.
Okay, compare that to the British type, or maritime Western Europe. Further north, 45–65 degrees. Cool, rain all year, 30 inches. Deciduous forests.
Right. These regions are firmly within the westerly wind belt year-round. Those winds blow consistently off the relatively mild Atlantic Ocean,
bringing moisture all year.
bringing moisture throughout the year, leading to frequent cloud cover and precipitation, often from those mid-latitude cyclones. And the influence of the warm North Atlantic drift current keeps winters much milder than they would otherwise be at these latitudes, preventing extreme cold. Hence, maritime influence is key.
But at the same latitude, inland, you get the central continental or Siberian type,
Yeah.
table says. Cold, light summer rain, 25 inches. Very cold winters. Coniferous forest, taiga.
Big difference. This highlights continentality. Being deep inside a large landmass, far from the ocean's moderating influence, leads to huge annual temperature swings.
Bitterly cold winters, warm summers.
Extremely cold winters because the land loses heat rapidly. Summers can be warm enough to trigger some convectional rain, but overall precipitation is lower than maritime regions, and the dominant feature is that extreme winter cold. This supports the hardy coniferous forests.
And finally, right up near the poles, Arctic or polar type, 65-90 degrees.
Cold.
Very cold, very little precipitation, 10 inches, often snow, tundra or ice caps.
This is pretty straightforward connection. Extremely high latitudes mean very low angle of incoming sunlight, insolation, hence very little heating leading to persistent cold. These areas are also dominated by the polar high pressure systems, cold, dense, sinking air which suppresses precipitation. What little moisture there is often falls as snow. Only the hardiest tundra vegetation, mosses, lichens can survive, or just permanent ice.
It really paints a picture, doesn't it? How the combination of latitude, pressure belts, winds, proximity to ocean, altitude, all those factors we discussed mesh together to create these very distinct climate zones across the planet.
Absolutely. Each climate type described in the source is a direct geographical expression of these underlying physical principles operating on a global scale.
And the type of natural vegetation listed for each zone, rainforest, desert scrub, tundra, is a direct consequence of that climate.
It's a powerful indicator. Plants are adapted to specific ranges of temperature and moisture availability. The vegetation reflects the climate.
So the lushness of the tropics or the sparseness of the desert isn't random at all. It's the living response to the conditions dictated by the global circulation of energy, air, and water.
Precisely. It shows the deep interconnectedness of the Earth's systems, atmosphere, hydrosphere, biosphere, all linked.
Well, that really was a deep dive. We've gone from the atmosphere's layers and the sun's energy through temperature controls, how rain forms, the global wind engine, storms, and finally seen how it all pieces together into world climates, all based on these textbook excerpts.
Yeah, hopefully tracing it from the fundamentals up gives a clearer picture of how climate science works, at least based on the core concepts presented in this text.
It definitely provides that foundational understanding. You see the physics and geography behind the weather maps and the different landscapes around the world. And, thinking about this whole intricate system, this dance of energy, pressure, water, it makes you wonder, doesn't it?
Wonder what?
Well, if the climate of any given place relies on this precise balance, the amount of insulation, the composition of the atmosphere, the position of pressure belts, the temperature of ocean currents, all those factors, what might happen if one of those fundamental components were to change, even slightly?
That's the critical question, isn't it?
Yeah. I mean, what does the sensitivity, we've seen how temperature changes with just altitude, or how different land and water heat. What did that tell us about the potential vulnerability of this whole complex global system if some core ingredient shifts, like, say, the amount of heat-trapping gases in the atmosphere, or the overall energy balance of the planet?
It certainly underscores how interconnected and potentially sensitive the whole climate system really is. Changes in one part can and do ripple through the entire structure.
Definitely something to think about next time you're checking the weather forecast or just feeling the air outside. Thanks for joining us for this deep dive.